which is going to be by Julien Le Sommer. And the title of his talk is going to be Why and How to Learn End-to-End Subgrid Closures for Atmosphere and Ocean Models. Julien, I can see your slides now in full screen mode. So please, when you're ready, take it away. Thank you very much.
Okay. Thanks. Thanks for having me here. Can you confirm you can hear me well?
Yes, indeed.
Yes, cool. I will try today to probably convince you that there's probably a case for trying to learn subgrid closures end to end, and it comes with a number of benefits. This presentation will be based on the work performed by Hugo Freza as part of his PhD project here in Grenoble in collaboration with my colleagues Ronan Fablet, Guillaume Balarac, Redouane El Gensat, and Anastasia Gorbunova. And I guess just as a start, we're all here because we're quite interested in trying to predict the evolution of those dynamical systems that compose planet Earth. And we want to do that with computers, but because obviously the resources for those computers are quite limited, we need, the only thing we can do is describe an approximate version of those equations. And as we all know, this implies that because of the nonlinearity of the equations of motions, we do have to close some terms. And we're very much aware that those closures, also known as parameterizations, are really key, as they are a rate controlling process in the long-term evolution of the system, and here examples of a number of processes that we need to account for. And we know it's a non-trivial and quite tricky problem because of its interplay with the numerical discretization, the number of processes we need to account for, the specifics of the anisotropy of the grids we're playing with, and the scale-dependent natures of those processes. So this has attracted quite some attention over the years, and recently indeed, and that's why we hear approaches with machine learning that have mostly been trying to either calibrate existing closures or accelerate their execution with emulation, and that's what we're going to talk about here, designing subgrid closures from data. So how is it you approach usually this problem? We've had a number of really cool talks showing this approach this morning. You basically start by choosing a model you like, a cloud resolving atmospheric model, the submesosphere permitting ocean model. You then define some sort of a projection procedure that allows you to compare your very high resolution trustworthy model with your low res coarse resolution model. Based on this, you assume some sort of a target for your low resolution model to behave as the projected version of the high res one. You build a database with the input, the outputs. Then you try to solve this supervised learning problem where you want to learn this missing flux from the actual variables you do have at hand in the low res model. Then you plug it back in your coarse resolution model and you pray. The reason why you pray is because the problem you're trying to solve is not the one you really care for. Let me be more precise here. We're trying to learn a correction to a model so that the time evolution of the system behaves as the time evolution of the high resolution system. But the way how we do that is only by looking at things over one time step. And this question is something that has been quite long ago described in the larger simulation community, and that's textbook science. So they call that the difference between the a priori skill and the a posteriori skill of subgrid closures. The a priori skills define the ability of a closure to predict an unknown term. That's something that you do at fixed times, while a posteriori skill is what you really care about, the impact over some time of the closure on the model solution. And surprisingly, that's to our knowledge something that hasn't been quite explored with machine learning approaches, which mostly deal with a priori learning procedure where you're trying to learn this mapping at fixed times, while you could think in principle of leveraging or formulating an a posteriori learning strategy where you try and optimize a component for your ocean model based on a loss for your climate model based on the loss that involves like several iterations over time. So that's what we've tried to address here with like really basic question: is it basically worth it? What are the benefits? And do we need to even think about that? So the way we decided to approach that was to try and identify a problem that would be like interesting and a bit challenging. We ended up deciding to probably use one of the most simple we could think of. So quasi-geostrophic turbulence. You all know the equations here. You all know that velocity dynamics that happens at planetary scale. It's somehow analogous to velocity dynamics in 2D incompressible Navier-Stokes equations. You have a conservation of vorticity and a number of invariants there, including energy and entropy. And under very generic conditions, you have this dual energy and versus entropy cascade, with the entropy being flux to fine scales and energy back to large scale. And it turns out that this problem is a surprisingly difficult problem for closures in general because of this energy backscatter, but also for machine learning based closures. And up to now, all the approaches for closing this problem with machine learning are really based on ad hoc procedure for solving this energy backscatter problem. So we do have an interesting problem here and lots of good benchmark problem. What we're trying to do here is really to try and learn a neural net based parameterization that could basically bring back our coarse resolution model to the high res one. And we want to do that. The first thing we need is a way to compare our high res and low res models, and we do that with some generic projection procedure. And once you've done that, you can formulate your equation for the low res component and start like playing the game of learning this closure. In order to play this game, you need a coarse resolution and a high resolution model. We've implemented it in PyTorch and decided to focus on three typical use case coming from the published literature. So force turbulence, decay turbulence, and a beta plane case corresponding to different like flow regimes with different properties. We decided to focus on two really well-known sort of filtering approaches for projecting the high resolution to the low resolution here, Gaussian kernel and cutoff projection. And the sort of flows you end up with look like this. So you have here a snapshot of the vorticity at the beginning of one of our forced turbulence experiments. And on the right hand side, what you have is here is the deviation between the filtered quantity and the full quantity. So what you see here is what we basically an indication of what we want to learn with the neural net. Number of different experiments, and the only number here maybe to remember is that we're playing on 2048 times 2048 sort of square boxes here, double periodic flows. Okay. In terms of the architecture and the training, what is it we're doing? So we're using something very simple in terms of the closure. We're using a 10 convolutional layer with ReLU nonlinear activation sort of networks. And the reason why we're doing this is because we're not here for getting the best possible closure. We're just here for comparing different approaches for training. On the one hand, we'll train this network with a loss that's based on the a priori training criteria. So standard sort of approaches, trying to learn this mapping to estimate the instantaneous missing term in the equation. And on the other hand, we're also trying to learn what we call a posteriori training strategy, where the loss is built out of comparison of the actual model state over several successive time steps. So we have this loss here that involves a model integration, but also the projection tau from fine grid to coarse grid. Okay, we will compare that with some baseline empirical closures, well-known one based on the AD viscosity sort of frameworks. On one hand, we will look at the Smagorinsky model that's based on the strain rate, and also compare that with the Leith model that you probably all know here, where the key quantity you want to get information from is the vorticity gradients. And obviously, we're using like all the fancy dynamic procedures that allow to get the best out of those AD viscosity closures. In terms of the performance metrics, as I said, we're in a really good situation here because we have benchmarks, and those benchmarks for the ocean modeling literature were set by Graham and Ringler about 10 years ago, and we'll be using the metrics here with metrics that deal with the domain integrated evolution, the evolution of the domain integrated energy and entropy, and also on the other hand, the cross-scale fluxes at equilibrium for both entropy and energy. So here we are all set for getting into the results. So this is the result of a forced turbulence case, what you see here. On the top left corner, you see our filtered DNS. So that's a snapshot of the filtered DNS. That's our target. And on the right-hand side, you see some results coming from the baselines on the top and our learned closures at the bottom. You see that overall, the empirical baselines look to be slightly over-diffusive. The solution seems to miss some fraction of the fine scale detail we do like. On the other hand, the closure that's learned from a priori criteria looks a bit ugly. And the reason for that is because it doesn't know how to really handle this energy backscatter. So it's a step towards an unstable behavior. We see here an accumulation of variance at fine scale. While the a posteriori closure that we've learned with the a posteriori procedure seems to behave quite well. A way to illustrate that a bit better is to look at those spectrum and cross-scale fluxes here for entropy. And if you compare a bit the sort of different approaches, the different models we do have here, you see basically the take-home message here is look how close my blue line is from my dashed black line. So on the left-hand side, you see the entropy spectrum. On the right-hand side, the flux. Seeing that you're fluxing towards fine scale entropy, and the rate at which you do that and the scale at which you start to do that is really well captured by our a posteriori procedure, while the a priori procedure seems to misrepresent this flux at fine scale, which leads to an accumulation of variance at fine scale. So that's something that we don't like. This was for the equilibrium state. You can also look at that on the decaying turbulence sort of case. And there again, what you see is that the time evolution of the integrated energy and integrated entropy shows that the a posteriori learning has a superior skill as compared to the a priori learning strategy. And what's interesting with this test case is that we're getting across a number of different regimes as the turbulence is being shut down by dissipation. You're really going across a number of regimes. So that tells you something about the ability of the model to generalize to different flow regimes. True for the decaying turbulence case and the beta plane turbulence case, same sort of behavior there again. The time evolution is really well captured by the a posteriori learning procedure. So what is it we've learned? One more point, the actual relative performance. One thing just like to make it clear to everybody here. So you can look at some metrics that really come from the a priori world, like things like the correlation between the missing term and the learned term. And if you do this business and compare the different procedures with different sort of filters and stuff, what you see is that overall, almost all the time, the best performance in terms of a priori metrics comes from the a priori learning strategy. While if you look at a posteriori metrics, like here, that's a metric that compares point by point the entropy flux in spectral space. And here, the smaller the number, the better. You see that the a posteriori strategy really leads to the best results. So there's nothing magic here. It's just like you get what you ask for. So the best a posteriori metric sort of closure is the one that you learn with an a posteriori learning procedure. So where is it we are here? What we've learned so far is that we're able to learn subgrid closures end to end. So really with the actual objective we really care about. And this involves what we call a posteriori training. And you need to integrate your model over several time steps. For the particular test case that we've looked at, it seems to solve this unstable behavior due to the energy backscatter. And it seems to outperform the baseline that we've considered here. So that's good. Now for the thoughts. Two thoughts. The first is I've cheated a bit here. I've really rapidly told you that I've used the spectral code implemented in PyTorch. Obviously, our climate models will never, or I don't know, but they will probably not be soon implemented in a fully differentiable framework. So we basically have two solutions here if we want to leverage that sort of approaches. Option number one is rewrite entirely our code and try and benefit from the automatic differentiation, because we need the autograd for computing the loss. So if we want to optimize our parameters, we need autograd. Option number two may be to try and use emulators, and that's something that we've tried and started playing in the group, and it seems to work pretty nicely, and I could discuss a bit more about that. Second problem, or second thing I wanted to raise, is the fact that we actually haven't invented anything here. If you think about that, like in terms of the math, the end-to-end learning is just simply a strong constraint for the VAR algorithm, where the control parameters are simply the parameters of your neural net, and your observation here are supposed perfect and non-noisy and dense. So that's a problem that we know. Therefore, the problem we're trying to look at here is very close to approaches that people are playing with in the right now, like this recent work by Farshi, where the authors try to learn state-dependent bias correction. That's basically what we're doing here, except that the way how we solve this is by directly integrating the neural net within the GS step. So what it really opens is probably the possibility to, in the end, think about really learning our models from noisy and incomplete data. And that's something that we could think about for the future. Conclusions, I guess I've added 2 points here. The fact that we may need to leverage differentiable emulators if we really believe that end-to-end learning is something that we need to go for. Second point, what we're doing here is very close to strong constraint for the VAR, which opens a lot of interesting connections from my perspective. So this talk was based on 2 contributions. One that was presented earlier last year at a workshop size NeurIPS, and there's a paper in preparation for GEMS that we're about to finish to submit soon on this. If I still have 20 seconds, I just wanted maybe to raise an additional point here. In my real life, I'm more a standard sort of a computational oceanographer, playing a lot and trying to contribute to the development of the NEMO ocean model. And therefore, I care a lot about the way how we will bring those neural net into existing legacy models. And I'd be very happy to discuss with you guys the question of the interface. We believe in our group here that we will need clean interface, and we're investigating what the smart sim interface could bring us. But beyond the choice of the interface, there's also the question of how we will share those model components based on neural nets. And I think we need a clear community efforts there for defining a bit how to work with those new tools. I thank you for your attention, and I'm happy to take any questions.
Wonderful. Thank you, Julien. That was a really interesting talk, although you did obviously steal my opening question about we don't have differentiable climate codes, but that's good. And also, just to touch on your last question in terms of interfacing, that's something we're thinking about a bit at ECMWF, so maybe we should have a conversation about that in the future. There are also some other questions in the chat, because sadly it's not just my choice to ask questions myself. So we have one from Peter Watson. How long were the trajectories used for posterior training, and how long could the resulting model stably run for compared to typical timescales of the system?
Okay, so I can give you the numbers and the rationale there. So what we've done here, we're integrating over 25 time steps of the coarse resolution model. So that's not much. We think, and we've tested, we think that we should be able to train with time step up to maybe 100 or 200 sort of windows. So that's you may say that's not much, but that's because we're really much limited by the fact that the optimization problem becomes very complicated if you're like stacking together so many steps. There are probably ways to workarounds to find them there. You don't need to propagate everything and stuff. But the key information we need to keep in mind is that the problem we're solving here has exactly the same constraint as a strong constraint for the VAR window. So basically, we should be able to formulate this with exactly the same sort of problems as a strong constraint for the VAR window. So typically for the atmosphere, I guess from several hours to one or 2 days.
Great, thank you very much. And we have another question from Clément Brochet, who is, did you try incorporating time evolution memory, such as RNN and LSTM, into your model so as to assess the a priori setting with time awareness and sort of approximating the a posteriori setting?
So certainly that would be something very interesting to do. Here we were really just interested in seeing whether at fixed computational complexity, whether we could gain something by just changing the loss. Obviously, once you've done that, you're just changing the way how you formulate the problem, and therefore you're free to reuse whatever information coming from the past that you want, which is not the way how we formulate the problem right now. I'm sure this could bring a lot of benefit, but we haven't investigated that here, and I'd be really happy to discuss that later during the discussion.
Yeah, no, that sounds really interesting. I think your a posterior can set a good benchmark, right, for what would be possible with a fully differentiable model that you can then try and aim for. Excellent. Right. Well, we've now, that takes us, thank you, Julien, now takes us to the coffee break. So if you consult your schedules, you'll see right now we have a 20-minute coffee break. And after that, we're going to be going into our poster session, which will be happening at GatherTown. So you should have been given a link as to how to connect to that. I encourage you to go, as I will be doing, to look. There's a small but interesting selection of posters there to check out. And then the next, and there'll be opportunities to discuss in there. So you might bump into colleagues and have some discussions on that platform. It works quite well, I think. But the next time we have some live presentations will be at 2 p.m. UK time or 3 p.m. European time, when we will have a talk from Rachel Ferner on developing an emulator of an ocean GCM. And also, hopefully, most of our speakers will be able to return towards the end of the day for a discussion of the various topics that we've been hearing about. So I'd like to thank all the speakers again. It's been a really interesting opening morning, and I will see you all in the poster session.